a box. Okay. See you later. Okay, so, yeah, well. Are we doing something different? Okay. Okay, so what we have for today is preparation for the midterm on Friday. So don't forget midterms on chapters 5, 6, 7, and 8 on Friday in class. The homework assignment. The homework assignment is due tonight. And what I'm planning for today is to start with the practice test and go over the entire practice test, which probably is going to take more than 50 minutes. So feel free to leave if you want to leave, or if you just get sick of it. That's also an option. Any questions? Yes. Recording it. I'm recording it, and I'll send the link to everybody that is in the mailing list. Okay. So again, the practice test has more questions that are not exactly conceptual, but questions that require calculations. This means that the midterm on Friday is going to have conceptual questions. Many of those conceptual questions are going to be from the homework assignments on chapters 5, 6, 7, and 8. You are also going to have some questions from the previous chapters, especially from the first midterm. But they're going to be conceptual. They shouldn't create a problem. But in case if you didn't study the problems from the first midterm, go over them again. It's a good exercise, especially problems related with Newton's second law, chapter 4. So any other questions? So the midterm, as always, the midterm is going to be doable in about 20 minutes, 20, 25 minutes. You're going to have extra time, but if you know the material, you should be able to finish the midterm in about 20, 30 minutes max. People that have that require special accommodations like quiet room and everything else that they may require, please find me in the office about 10 minutes before the test, and we're going to find a place for you to work. Okay. Any other questions about the test? If not, we're starting with problem number 1. It is a problem with circular motion satellites. Oh, by the way, somebody asked me to put in the test problems similar to homework problems 6 and 8 from chapter 6. So problem 6 from chapter 6 is something like this. You have loop-the-loop problem, object that is up there. What should be the speed of this object on the top? So this is a very trivial question, and you may have a question like that depending upon what your version of the test is. But that question is going to be differently formulated, and this loop-the-loop situation may be just part of that problem. The problem itself may be something more, something bigger, like like finding speeds and something of that matter. If you, let's say, start from some certain height, what height do you need to start from rest or with certain speed in order to have the required speed you have to make it around the loop, or something of that nature. Problem number 8 from homework 6 is the problem about the caloric value of exercise. Or it was person that is bicycling many miles, and how many calories does he burn in this process. A problem like this you're not going to have on this midterm, because it is a problem more related with not with physics, not completely a physics problem. So it would be a good problem if we had some amount of thermodynamics in the class, but thermodynamics comes later. So that problem, I gave it in the homework assignment just to know that in addition to joules, you have widely used units for energy like calorie, kilocalorie. So this was the purpose. So now problem 8 on this midterm. So knowing all of this, let's start with problem number 1. Let's start with problem number 1 from the homework, from the practice test. You have a satellite going around the planet. So here is the planet Earth with mass capital M, and here is the satellite going in a circular orbit. So this is the radius of the circular orbit, and you want to determine the circular orbit in such a way that the satellite should do 5 revolutions in 24 hours. So this problem is relatively, it requires several steps, not a single step. First, here, start with the diagram like always. The satellite at certain moment of time could be here along the circular orbit. The only force that acts on the satellite is the gravitational force directed to the center of the planet Earth. So that gravitational force as a single force, net force acting on the satellite, that gravitational force should act as a centripetal force. And any centripetal force is equal to mv squared divided by r. So if the mass of the satellite is lowercase m, that centripetal force, like any other centripetal force, is mv squared divided by r, where v is the speed of the satellite. On the other hand, that force is gravitational force, and it also should be given with the universal law of gravitation. So the force, the gravitational force, is equal to constant of proportionality times the product of the masses divided by the distance between the center of the planet and the satellite squared. So from here, the force is expressed in 2 different ways. Well, if the left-hand sides of those two equations are the same, the right-hand sides also have to be the same. In other words, you must have mv squared divided by r equal to gravitational constant, mass of the planet, times mass of the satellite, divided by the radius of the orbit squared. And here you cancel the mass of the satellite. You cancel 1 power of the radius of the orbit. And on the left-hand side, you're left with the speed of the satellite squared. So it is equal to gm divided by r. So look, you still cannot plug in numbers. You don't know the speed, you don't know the radius. And this is actually why I gave this problem, because it makes you work with formulas rather than with numbers. You just don't have the numbers. Well, so this is one expression that we have. That expression connects the speed of the satellite, unknown, and the radius of the orbit, also unknown. We haven't used yet the fact that the satellite does 5 revolutions in 24 hours. In other words, they tell us something related with how much distance the satellite covers in certain amount of time. In other words, they give you something like velocity or something of that nature. So, well, the speed of the satellite should be the distance covered. So you cover 5 circumferences of the orbit, 5 orbits. So it is 5 times 2 pi the radius of the orbit. So this is the distance covered. It is the opposite. Let me correct that. The speed of the satellite is proportional to the distance covered. Actually, that distance is given, right? Okay, let's write it again. 5 times 2 pi r squared divided by the time during which this distance was covered. What is the time? It is 24 hours, right? Divided by 24 hours. Unfortunately, if you use this expression, you're not going to work with SI units. Hours are not SI units. So you have, in order to get the speed in meters per second, you have to convert this 24 hours into seconds. In other words, each hour is 3,600 seconds. So 24 hours is going to be 24 times 3,600. And this is going to, yeah.
I'm still confused why you can put the 5 up there and not 5 up.
They say
it's 5 times, not like
yeah, look, 1 revolution is 2 pi r. They say that you cover 5 revolutions. Well, I'm just how long is 5 revolutions? Basically, this is what, because the satellite covers 5 loops. Right, this is what you can make the argument in many other ways if you feel like. In the textbook, they introduce period of the rotation of the satellite. I just and when I talked about satellites, I also used the period. But now I'm gonna stimulate. Well, it doesn't matter how you do the reasoning. What matters is the reasoning to be done and to be clearly presented and logical. I don't know how clear is this, but speed is equal to distance covered. This is not r squared. This is just 2 pi r. Distance covered divided by time is the speed, right? This is one way to handle it. Yeah,
So if we did have it in radians, would we just put the radians on top and then divide it? We would do it, we would times it by 2 times. Right?
this is, so you can solve this problem using angular velocity. But I started with linear velocity, that's also going to work. So when we covered satellites, we didn't have the concept of angular velocity yet. But of course, you can solve this problem using angular velocity, and it's going to be perfectly fine also. So if you keep going this way, what are you going to do? Well, now combine this expression for the speed with this expression for the speed. I can plug in the speed expressed this way right here, and I'm going to have this 5 times 2 pi r divided by 24 times 3,600 squared is equal to the gravitational constant times the mass of the planet Earth divided by the radius. And now in this expression, the only unknown is the radius of the orbit, and I can determine it. So how to determine it? Rewrite the left-hand side, let's say, rewrite it like this. 5 times 2 pi divided by 24 times 3,600 squared, r squared. I just isolated r on the left-hand side. On the right-hand side, you have divided by r. And after that, this r from denominator comes here as a nominator. This goes to the other side of the equation in denominator, and you get the result. And the result looks like this. So the result is going to look like r cubed is equal to gm divided by 5 times 2 pi divided by 24 times 3,600 squared. And therefore, the radius of the orbit itself is cubic root of this entire expression. So you can say the radius of the orbit is, well, you can rewrite it in multiple different ways. I'll leave it the way it is. Gm divided by 5 times 2 pi divided by 24 times 3,600 squared, all of this to power 1/3. Power 1/3, of course, is cubic root. So this should be the numerical answer. And you have to read the gravitational constant and the mass of the planet from the formula sheet that is going to be provided. So this is a relatively long problem. It is not a problem that is good for multiple choice conceptual type of questions. But the problem is given in the practice test because it asks you to figure out centripetal force, Newton's law of gravitation from chapter 4, and after that, do the algebra conversion of, well, the period of rotation, express the speed in terms of period of rotation. And again, the problem can be solved in multiple other ways, like using angular velocity rather than linear velocity, but the result is should be the same. Any remarks?
Is it possible that this question might be one of the long questions that we get on the test? Like the
So look, if I so I already somebody asked me to do the problem with the truck that is sliding downhill. and find the braking distance or find the coefficient of friction depending on, or find the initial speed of the truck, right? This was one of the problems that we did in the homework assignment, and also it is in the practice test. I don't know which number of the practice test. So I promise that problem to be one of the calculational problems on the test, only for people that want that problem. So when you're getting the papers, say, I want a version of the problem with this sliding track. And you're going to get that problem, but you have to write the solution step by step very carefully. So in a sense, we already have one of the calculational problems. I don't want to write more than 3 versions of the test. So for the moment, we're kind of set, but you have one problem that you can run and request that problem. So the problem with the truck sliding downhill, it can be formulated in multiple steps, guiding you through the solution. But you have to understand each step. Or it could be just directly stated like it was stated in the homework assignment. But instead of asking you what was the initial speed of the truck, or what is the stopping distance, you may be asked something else, or the truck may be going uphill instead of downhill. So there are multiple variations of a problem of this type. But if you understand one version of this problem, you should be able to write down clear solution of any other variation of the problem. Okay, how many people are thinking about learning that problem and requesting a version of the test with that problem? Okay, that's good. Well, once so we're going to solve it again. It is in the practice test somewhere. It's one of the practice test problems. Okay. Any questions here? If not, let's go to the next problem. It is about collisions between a hammer and a nail. And in this problem, you just have to, again, you have to realize what is going on. So the hammer is coming in vertically down with speed that is given, V initial, let's see. And after that, immediately after the collision with the nail, it goes up with speed V final. So all the vectors in this problem are in the vertical direction, so vector signs are not needed. However, you need a coordinate system. And if you choose a coordinate system like this, with positive direction of the vertical axis up, this means that the initial velocity of the hammer is negative 4.5 meters per second. Negative 4.5 meters per second. And the final velocity is positive 4.5 meters per second. So this type of problems requires you to be able to introduce negative and positive momenta, velocity, and so on. And after that, you can directly answer this problem by recalling that Newton's second law, which usually we express as force is equal to mass times acceleration, net force is equal to mass times acceleration. You recall that alternative way of writing Newton's second law is to say that net force is equal to the change of linear momentum divided by the time interval during which this change happens. In other words, for our version, you're going to say this is the change of linear momentum is final minus initial linear momentum, And I'm going to start skipping the vector science because all the vectors are in along the y-axis divided by time interval. So the final linear momentum is mass times final velocity. Initial linear momentum is mass times initial velocity. Velocities are given. The masses are given, right? In other words, it is going to be an expression like this: mass times v final minus v initial divided by the time interval delta t. And therefore, you can say that, well, from here on, it is only numbers. So this is mass times 4.5 minus 4.5 divided by the time interval. In other words, it is mass times 9 divided by whatever the time interval for the collision you have. So it is, this problem is pretty much conceptual because you can directly start. I talked a lot and I wrote a lot, but you can directly do this. Again, the homework assignments are going to be a very good source of conceptual problems that don't require even use of calculators or substantial use of calculators. Okay, any questions about this problem? If not, let's go to the next one, problem number 3. A string breaks when the tension reaches 400 newtons. And here is the equation that we're talking about. So here is the string, and it is going in a circle like this. And they're asking us to figure out the speed with which you can do. This stone or this ball is going to be moving just when the string breaks. So this is another problem related with circular motion. And what you have to do in this problem, so this is problem number 3, you have to realize that if you look from above, the trajectory of the object looks like this. Here is the string, here is the object. The radius of the trajectory is given. So, of course, there is a gravitational force perpendicular to the board, but the gravitational force is not relevant here because it doesn't provide any centripetal acceleration. The only force that is responsible for the circular motion is the tension from the string. Call that tension F. The tension from the string F. And since it is a centripetal force, it has to be mv squared divided by r. In other words, the force is mv squared divided by the radius of the circle. The maximum value of the force that the string can provide is given. The corresponding maximum value of the speed is in this expression. So you just have to solve for the speed. So from here, the speed is going to be square root of the maximum force times the radius divided by the mass, everything under the square root. And this should give you one of the numerical answers that are in the practice test. Okay, remarks, questions? If not, let's go to the next problem. Problem number 4, you have a car that is going in a horizontal curve, not banked. So the car is relying only on the friction force, static friction force, in order to make that turn. So this is what you have. Here is the curve. the center of the circular path is somewhere here, and the car is right here. So the forces that act on the car are the weight, completely canceled out by the normal force, and the only other force that is left, and it is directed to the center, if is the static friction force, F static right here, directed to the center of the turn. Right, remember that the static friction force is marked force. It gets directed according to in which direction, in opposite direction to the direction in which the object wants to move. Well, the object wants to escape from the circular path, wants to keep going along a straight line, and one fraction of the static friction force is keeping it on the circle. So in other words, this static friction force should be centripetal, mv squared divided by r, where r is the radius of the turn, right? This is r, is right here. What is m? The mass of the truck, or the mass of car, or whatever it is, right? It is car, the mass of the car. So now look, they're asking about the maximum speed. Therefore, the maximum speed is going to occur when you have the maximum value of the friction force, static friction force. And you know that the maximum value of the static friction force is coefficient of static friction times the normal force. But if this is the pavement and this is the car on the pavement, you have the weight downward, you have the normal force upward. The car doesn't go up or down. And therefore, the two forces in vertical direction have to cancel out, which means that the normal force must be equal in this situation to the weight of the car. In other words, this makes the maximum value of the static friction force a coefficient of static friction times mg. And now, on the left-hand side, you have the same force, the static friction force. Therefore, the right-hand sides also have to be equal. In other words, mv squared divided by r should be equal to coefficient of friction times mg. The mass of the car cancels out, and you get that the maximum speed v is equal to square root of coefficient of friction times 9.8 times the radius of the curve. All of this under square root. Okay, any questions, remarks, issues? So in this problem, you need to know centripetal force, and you need to know from chapter 4 that the maximum value of the static friction is coefficient of friction times normal, and you need to realize that the normal force in this situation is equal to the weight in magnitude. Okay. If no questions, let's go to problem number 5, which is similar, but now instead of a flat curve, the pavement is banked. It has to be banked like this, right? To the inside of the turn. And they're asking you what should be the banking angle in order you to be able to make this turn without relying on the friction. So probably the road is icy, and you need to take the turn with some high speed, 66 miles per meters per second is what? It's very high speed, right? So it is 66 is probably something like close to 120 miles, I guess, per hour, or something of the order of 100 miles per hour. So this is high speed.
147
Miles or kilometers?
miles.
Wow. But you see, once you learn physics, you're going to be able to drive with the speed on the highway. Right? It's probably not going to work with your electric bike. What is the maximum speed of your electric bike?
20 miles an hour. But going downhill.
But you know, this entire concept of electric bikes, it is kind of cheating, right? Instead of suffering uphill,
Both
plus
ways.
pedals, yeah, both ways uphill, yes. Okay, well, I suspect that you cannot reach the speed even with your car. Are you driving a Porsche or what are you driving?
A Focus.
Yeah, I don't know. Cody is kind of not very reliable person to do physics experiments with high speed, right? Look, you go to your parents and you say that for this physics class, you need a car that can do 200 miles per hour. I would recommend something like, well, if Porsche is a little bit too pricey, you can go for something else like what? Anybody? Any ideas for Cody here? I think that I hear that Lamborghini is quite good.
Want to look up how much Porsches cost?
It depends, I guess. I guess that you can find on eBay some used Porsche at the price of a Ford Focus. You should be able to, right? Yeah. So what? Look, don't look at the price. Let your parents look at that and don't scare them from the beginning. But if it is a requirement for school, right? They should help with school supplies, right? So give it a shot.
Yes.
And let us know if it works. Okay, so here is the pavement of this curve right here, and the car is right here. And the center of the circular turn is somewhere here. So in other words, well, I'm not going to draw the radius, but the radius of the circle is this distance. And what you have to do is, let's make this pavement a little bit bigger. So you're looking for this banking angle, theta, the angle between the pavement and the horizontal. And what you have to do is you have to draw carefully a free body diagram. There is no friction, so there are only two forces present. The weight, which is vertically downward, and the normal force, which is perpendicular to the surface of the contact between the car and the pavement. So you may be tempted here to decompose the weight into components, but don't do that. It's not going to help you. You need a component of the forces that acts in direction to the center, a component of the forces that can be centripetal force. The weight is perpendicular to the radius. Here is the radius of the circle. The weight is not in the right direction. It doesn't have, it has 0 components in radial direction. So you have to use a component of the normal force to act as a centripetal force. And the weight has to be canceled out. So just imagine that this normal force is a little bit bigger, so it should to be easier to see. Here is the normal force. And now decompose this normal force into a component that is going to cancel, the weight, and the component that is going to act as a centripetal force. Here are the two components of the normal force. This is Fy, vertical component, and this component is in the correct direction, right? This component acts at the center of mass of the car, so it acts right here. That component, call that Fx, that component is the centripetal force. So you want to cancel the vertical forces so that the car not to go this way or this way. And the only uncancelled force is going to be this component of the normal force. It is directed to the center. It is going to be your centripetal force. Yeah.
So is the centripetal force always going to be looking for whatever the x direction is, whatever that is?
Well, it is x here is not exactly the right notation. I would say when you're talking about circular motion, you better talk about tangential and radial components. So Fx, strictly speaking, well, you can introduce any coordinate system you want, but you want radial direction, radial component. And this is why in circular motion, the convenient coordinate system changes from moment to moment as the object goes around the circle. In our case, we said the vertical component has to be equal to the weight in order to cancel out. It already has direction opposite to the direction of the gravity force. On the other hand, we said that the horizontal component, the radial component, has to be centripetal, therefore it has to be mv squared divided by r. So in this problem, we're looking for the angle. And well, the angle so far is nowhere in our equations. But if you look at the diagram, you're going to realize that the banking angle of the rod is exactly equal to this angle of the right triangle formed by the two components of the normal force. Because that angle and this angle are angles with mutually perpendicular arms. This dashed line is horizontal, so it is perpendicular to the vertical. And this line is the pavement, which is perpendicular to the normal force. So from this triangle, you can say that, let's say, that the y component, let's say, this one, is equal to the hypotenuse, which is the total normal force, F normal, multiplied by cosine of the banking angle theta. And now, if you look at this in this equation, the left-hand sides are Fy the same. Therefore, you can say that F normal times cosine of theta is the same as mg. And therefore, you can say that F normal is determined to be mg divided by cosine of the angle. Again, you cannot plug in numbers because the banking angle is not given and the mass of the car is also not given, so you cannot get a number here. But they're asking about the banking angle, so banking angle finally appeared in our equations. You go to the second equation about the radial component of the force. And again, looking at the diagram, you see that the radial component Fx is equal to the hypotenuse of the right triangle times sine of the angle theta. In other words, from the left-hand sides are the same, therefore right-hand sides also have to be the same. So you have from those two equations, you have that F normal times sine of the banking angle theta could be mv squared divided by the radius of the turn. And now recall that you already know an expression for the normal force. This is the expression that you have for the normal force. Substitute it here, and you're going to have mg divided by cosine of the angle multiplied by sine of the angle is mv squared divided by r. You see that the mass of the car cancels out, and you're left on the left-hand side, sine divided by cosine is what? Tangent. So on the left-hand side, you have tangent of the angle that you're looking for, and that tangent of that angle is equal to right-hand side divided by 9.8. 9.8 comes here in denominator, so it's going to be equal to v squared divided by g times r. And this is the tangent of the angle. The angle itself should be equal to inverse tangent of v squared divided by g times r. And there should be the answer. This problem, again, is multi-step problem. And it, again, makes you work with formulas rather than with numbers. And this is why this problem is in the practice test. And this problem, of course, is an example in the chapter that first introduces rotational motion. Okay, so of course, if you have to leave, please feel free to leave. And I'm going to email a recording of this problem solving session. And okay, I'm going to continue now with problem number 6. Problem number 6. Problem number 6 says that you have an object that is sliding and eventually reaches a point in which it has to go along part of a circular path. So a point like this. Let me draw it. Here is the point A, which is on the diagram on problem number 6. So they're asking you to figure out what is the normal force at that particular point. And what you have to do is, here is your object, you have to show a free body diagram. This is the only. So you have the weight acting vertically downward, you have normal force acting vertically up in direction to the center of the circle. The net force acting on this box is normal force minus mg. This is the net force. And since you want this object to be moving along part of a circular trajectory, it could be infinitesimally small part of the circle. But at that moment of time, that net force must be centripetal. In other words, it must be mv squared divided by r, where r is the radius of the circle. And from here, you can say that the normal force is mv squared divided by r plus mg. So this problem is given in order you to realize that the normal force is not always mg. It depends upon the conditions of the problem. In this case, it is not. Any remarks here? If not, let's go to problem number 7. In problem number 7 is similar to the problem with this rock rotating in horizontal circle. So problem number 7, you have a circular path of this object. So of this mass, they give you the value of the mass, and this is the trajectory looked from above. So the weight is in downward direction, the normal force is in opposite direction, and they exactly cancel out. It is a horizontal surface. So if the object is here, the only force that acts on this object, the only force that is not canceled is the tension of the string. Call that tension F. Well, they don't ask for something else, but they ask for the time for one complete revolution, which means that you have to find the speed of this object. So the velocity is this way, right? This is the velocity vector. So they give you the mass, they give you the length of the string, which means the radius, and they give you the tension. So they give you the value of the force F, of the centripetal force F. That centripetal force is centripetal force, so it is mv squared divided by r. So here the force is known, the mass is known, the radius is known. The only unknown is the speed, and you can find that speed. V is going to be equal to square root of F times the radius divided by the mass of the object. Well, once you know, so this can be calculated as a number, but don't hide it. Now, let's see to answer their question. The time needed. Well, the time for one complete revolution, that time is called period, and that time is proportional to the distance covered, and the distance covered for one revolution is 2 pi r divided by the speed, which is the expression that we just calculated. So for the time for one revolution, you get 2 pi r divided by square root of F times r over F. And you can simplify a little bit this, but you can leave it also this way. Okay, questions? No questions. Let's go to the next problem. Problem number 8. Orbital speed of an ice cube rotating on the rings of Saturn. So again, this is a problem similar to the previous satellite problem. So you have to do two things. You have to say the net force acting on this ice cube is centripetal, but it is also gravitational force weight. And therefore, and this is going to solve the problem. So you have a situation like this. Here is the circular path. So circular path. The planet Saturn is with given mass m, and you have the radius of the orbit is given. Call it r for the radius of the orbit. So this ice cube is moving with unknown speed v that you have to determine. The unknown speed of this ice cube, like this. So we said the net force is gravitational force. So this is the net force acting on the ice cube. And actually there are no any other forces present, only the gravitational force. So since it is a gravitational force, it should be equal to universal gravitational constant, the mass of the planet Saturn, times the mass of the ice cube divided by the distance between them squared. On the other hand, that same force has to be centripetal to, and therefore it should be equal to the mass of the ice cube times v squared divided by r. From here, the left-hand side of each of those equations is the same. Therefore, the right-hand sides also have to be the same. And therefore, you can say mv squared divided by r should be equal to capital G times the mass of Saturn times the mass of ice cube divided by r squared. From here, the mass of the ice cube cancels out. 1 power of the radius cancels out. And on the left-hand side, you're left with the speed of the ice cube squared is equal to gravitational constant, mass of the planet Saturn divided by the given radius of the orbit. And square root of that expression is giving you the speed of the ice cube. So you have to be careful with the units. You have to probably, it is a good practice to convert everything into meters. So the radius of the orbit has to be in meters, just not to make a mistake. And this is going to give you the speed in meters per second, so you have to convert it back into kilometers per second. But this ensures that you're not going to have a mistake with the units. Okay, any questions? If not, let's go to problem number 9. Problem number 9. So you have a person that is in space, no gravitational force of any significance, and he is in a collision course with this spaceship. You don't want to collide head-on with anything. So what do? You take a book and you launch it in appropriate direction with appropriate speed, and this is going to presumably stop you from colliding. Okay. So what they're asking, what should be the direction and what should be the speed of this launched book? Make sure that this book is not a physics textbook. Otherwise, it's not going to work, right? You don't know physics, you won't be able to calculate how fast you should launch this book. But look, if you're moving this way and the spaceship is in front of you, you better launch the book exactly in the same direction, so the recoil to push you back and eventually stop you. So here, what matters here is that it is an isolated system of a person plus book, and you want to use the conservation of linear momentum. So you want the linear momentum of the system before the launch, initial linear momentum, to be equal to the linear momentum of the system after you launch the book. Vector signs are redundant here because all vectors are going to be along the line connecting the person and the spaceship. Well, the initial linear momentum of a person plus book is the mass of the person plus the mass of the book, so call the mass of the person capital M, the mass of the person of the book lowercase m. So this is the total mass multiplied by initial velocity v initial should be equal to the linear momentum of the system after the launch. Well, you want after the launch your body to be at rest. In other words, your body is going to contribute 0 linear momentum, but the book is going to be flying in the same direction, and it is going to have linear momentum equal to the mass of the book times the unknown speed v final of this book. And from here, you solve for the unknown speed v final, and you find that the speed of the launched book has to be equal to m plus m divided by m multiplied by the initial, and this should be the answer. Yeah, very simple, but very useful in case if you're planning to fly in space. Any people with plans like that here? Well, they were talking about the mission to Mars. So don't lose hope. You're young enough, maybe if you enter the lottery about this mission to Mars. Unfortunately, it is one way, I think, right? You go to Mars and you stay there. You don't have the ability to come back. But in case if somewhere along the way you end up in a situation like this, you know what to launch, in what direction, and with what speed. Right? Okay. Any questions? Yeah.
You just because you want velocity final to be 0, you just set it equal to 0, right? And then
So the final velocity of the person is 0. So the mass of the person times his 0 velocity is 0 momentum, right? This is all 0. But the momentum of the launched book is not 0. It is moving. The book is launched in direction to the spaceship. In other words, this launched book takes away all of the momentum of the system. No momentum is left for your body, and you're at rest with respect to the ship. Very simple. Very simple question. Okay, other questions? No? Let's go to problem number 10. Okay, so problem number 10 is one of the conceptual questions that you have to understand very well. So here is some object, and it may be rotating. The axis of rotation could be here, or it could be somewhere in the object itself. Do all points have the same angular speed? Well, look, if this is the axis of rotation, if you consider a point right here and the point right here, in 1 second, this point is going to cover this arc, while this point is going to cover an arc that is much, much bigger. In other words, points that are farther away from the axis of rotation are moving faster with faster linear speed. And you know that the linear speed is angular speed multiplied by the radius of rotation. So the radius of rotation here is R1, the radius of rotation here is R2. However, the two objects cover the same angle. Here it is the same angle exactly. So they have exactly the same angular speed. So the answer should be the same angular speed, but not the same linear speed. The linear speed is higher for objects that are farther away from the axis of rotation. Is it possible to drive in a circular path in such a way that you have non-zero tangential but zero centripetal acceleration? So look, tangential acceleration tells you if you're speeding up or slowing down along the circle. If you keep the constant speed along the circle, your tangential acceleration is zero. So it is completely possible to drive with non-zero tangential acceleration. You just have to change your speed along the circle. But the centripetal acceleration describes the change of direction as you're going along the circle. And if you go along a circle, the direction of motion changes all the time. Therefore, the centripetal acceleration for a circular trajectory has to be always non-zero. So the answer is you cannot have a centripetal acceleration that is zero and still do circular path. Not possible. The tangential, you can have anything that you want. It could be zero, negative, positive number, doesn't matter. All those options are possible. Okay, any questions? If not, let's go to problem number 12. Problem number 11. Oh, this was problem number 11, right? Centripetal and tangential acceleration. Now, problem number 12. So you have a circular disk with given radius, rotates with constant angular acceleration. So it is speeding up, moving faster and faster. What is the tangential acceleration of a point on the edge of the disk when the angular speed is given? So here is the disk. And here is a point on the edge of the disk. Well, look, they give you some numbers. You don't need to use every number that they give you. For this problem, you just remember that the tangential acceleration, the tangential part of the acceleration, is equal to the angular acceleration multiplied by the radius of rotation. And the radius of rotation is the radius of the disk. The angular acceleration is given, and therefore multiply them, and you're going to get you're going to get the value of the tangential acceleration. In other words, you don't need to use the value of the angular speed here. Now the units, if you want this formula on the board to work, the angular acceleration alpha has to be in radians per second squared. And it is given in radians per second squared. So you don't need to do anything. Just multiply those two numbers and you're going to get the tangential part of the acceleration in meters per second squared. On the other hand, the centripetal part of the acceleration, which they don't ask about, is going to be v squared divided by r or omega squared multiplied by r. Omega is given, but it is given not in right units, in revolutions rather than radians. But you know, 1 revolution is 2 pi. So 1 revolutions per second is 2 pi radians per second. So if they ask about centripetal acceleration, you can immediately say that it is this expression. Just convert the angular velocity into radians per second. Any questions, any remarks? Okay, problem number 13. Okay, so here in problem number 13, you have a question similar to problem number 6 from homework 6, because it is loop the loop. But it is different, I guess. So let's see what they say in this problem. So you have loop the loop, and they give you the radius of the loop. What should be your minimum speed so that you can make it around the loop without falling? Well, it is kind of trivial question, but here it is. Here is the loop with known radius. Here is the object at the top of the loop. Up the top of the trajectory is under the surface of the loop. So you're looking for the minimum speed. And when you're with this minimum speed, you're on the verge of falling from the loop, the verge of losing contact with the loop. And if you're losing contact with the loop, the normal force should practically disappear. You're practically barely touching the loop. The only force that is left is the weight. It is directed to the center, so it is net force also. It should be centripetal. In other words, mg has to be equal to mv squared divided by r, where v is the speed of the object at that instant when it is on the highest point of the loop. And from here you cancel the mass, and you get the speed required is equal to square root of r times v. So it is very simple, probably not. The units are normal, so you're going to get the speed in meters per second. This is disappointingly simple question, but it is exactly like question number 6 on the homework assignment on chapter 6. Okay. Problem number 14. Any questions about 13? If not, let's go to problem number 14. So you have a force that accelerates an object with given mass from rest along a horizontal surface, and it keeps going for a distance 20 meters. What is the final speed? How much work is done? What is the coefficient of friction? Well, let's do the diagram. Here is the object. So the force is horizontal, I guess. The force has to be horizontal. It has to be said. Otherwise, if they don't give the direction of the force, well, you cannot find the final speed, but you can figure out. Okay, so horizontal force with given value. Here is the force, the horizontal force. Of course, you have normal force, and you have the weight. The weight and the normal force are going to cancel out. The net force is the pulling force F. So what is the final speed of the cage if you start from rest? So probably the easiest way to answer this question would be force is equal to mass times acceleration. Find the acceleration. The displacement covered is given, right? It keeps going for this displacement X. So you can do it kinematically with Newton's second law, or you can do it in terms of energy. So let's start kinematically with Newton's second law. So all the forces that matter and displacements are horizontal, so we don't need vector signs. And I'm just going to say that the net force, which is the horizontal pulling force, the other two forces canceled out, is equal to the mass times the acceleration. And therefore, I can say that acceleration is now known. Because they give you the force, they give you the mass, the acceleration is their ratio. And now, think in terms of kinematics. You just figured out the acceleration. You know that the displacement is 20 meters. So another given number. And you know that the initial velocity is 0. So you have your three numbers, and you can answer what is the final speed. You need a formula that doesn't include the time for this motion. And that formula is the fourth kinematic formula. In other words, you use v squared is equal to v initial squared plus 2 times acceleration multiplied by displacement. Initial velocity is going to be 0, acceleration calculated, x is known, and the speed is this. So final velocity is square root of 2 times acceleration that you calculated times the displacement. So this answers question number 8. Any remarks so far? So we did it kinematically, but the next question, how much work is done? So we have to think in terms of work. And in this situation, it is an easy question to answer because the definition of work of a constant force is magnitude of the force times magnitude of displacement times cosine of the angle between them. The angle between them is what? Well, force is this way, displacement is the same direction, angle is 0. Cosine of 0 is 1. In other words, the work is going to be force times displacement. 300 times 20. This is the work done by the force in newtons, in joules. If the force is in newtons, the work done is going to be in joules because the distance is in meters. What coefficient of friction would be required to keep the crate from moving? to keep the crate moving, actually, to keep the crate moving with constant speed. Well, now in your free body diagram, you have to add a friction force, and it is kinetic friction because the crate is moving, but it is moving. The crate is moving with constant speed. Therefore, the crate is moving with what? Zero acceleration. So you have to show this line of reasoning. So you have to say V is equal to constant. Therefore, acceleration is equal to 0. Therefore, the net force has to be equal to 0. Therefore, the x component of the forces, F net x component has to be equal to 0. But looking at the diagram, the net force in x direction is the pulling force minus the friction. 0. In other words, you want the friction to be equal in magnitude to the pulling force of 300 newtons. But you know that friction forces, kinetic friction, is always equal to the coefficient of kinetic friction times the normal force. And you know that the normal force in this situation is equal to the weight because it is horizontal surface and no acceleration in vertical direction also. Therefore, the net force in vertical direction is 0, and therefore the normal force is just weight. So you have that the kinetic friction force is coefficient of kinetic friction times mg. And from there, this substituted here, and you're going to have coefficient of kinetic friction times mg should be equal to the pulling force F, and therefore the coefficient required, the coefficient of friction that is required, is equal to the ratio of the force divided by mg, and this should be the answer for part C. So it is important to show this type of reasoning. This word that says constant speed of motion implies 0 acceleration, which implies 0 net force, which implies each of the components of the net force be 0. Okay, questions and remarks here? Okay. So the next. So this was problem 14. Problem 15 is the truck problem, the homework problem with the truck. That we said that is going to be part of a version of the test that you can request. Problem number 15. But on the test, the problem is going to be most likely modified to show that, to check if you understand this type of problems. So in this problem, you have the truck that is traveling with given speed here in downhill, and it starts sliding. They give you the incline angle, and they give you the coefficient of friction, kinetic friction. What is the stopping distance? This is what they're asking. And again, this problem you can solve kinematically, or you can solve it using conservation of energy. Since we learned about energy in more recent chapter, chapter 6, I think. No, 6 or 7. Let's use energy, the work energy theorem. So here is, you have the hill, here is the truck on the top of the hill, and here is the horizontal. Let's say that the truck comes to a stop right here. This point, right at this point. They give you this angle of incline for this problem. It's 17 degrees, but I just will call it angle theta. They give you the initial velocity of the truck. So you have the initial is given 11 or whatever number of meters per second. And at this point, the truck is at rest. So the final velocity here is 0. They're asking us to figure out this distance. And if you start with conservation of energy, you have to, well, energy is not conserved. You have friction force that is constantly changing the kinetic energy of the truck. So you have to, the basic formula for the case when external forces change the energy of the system is that the change of energy, delta E, has to be equal to the work of the friction force in this case. In other words, you want final energy minus initial energy to be equal to the work of the friction force. And now, if you take the zero height to be at the place where the truck is at rest, in other words, you use a coordinate system. Well, let's stop. Let's not do coordinate system at this point. I'm going to add the coordinate system in a minute. But the zero, the origin of the coordinate system is at the point where the truck is at rest. So this is useful to make sure that the final energy of the truck is 0. So you have the truck is at 0 height and also with 0 speed, so it has 0 energy, mechanical energy. The initial energy of the truck, when the truck is up, has gravitational potential energy plus kinetic energy. So the kinetic energy is 1/2 the mass of the truck times the initial speed squared. This is the kinetic part of the energy. And the truck also has some height, which I'll call h. And therefore, it is going to have gravitational potential energy mgh. But h, this height is not given, and it can be expressed in terms of the length that you're looking for. The length that you're looking for is this length. So if you call that length x, in other words, I'm using a coordinate system that has y-axis this way, x-axis this way. And the origin, of course, we said is at the stop point. So the distance x is from here to here. This is the distance that you're looking for. This is the displacement of the truck that you're looking for. And you can say that the height, the initial height of the truck, is equal to the hypotenuse of this triangle. This is a right triangle that is formed, multiplied by sine of the angle theta, like this. Which means that you can say that the initial energy of the truck looks like this. 1/2 mv initial squared plus mg multiplied by x times time of the angle of the incline. Okay, so now we have the change of energy. This is this expression with minus sign. Now we have to figure out the work done by the friction force. And to do that, we need a free body diagram that is clear enough. So you have the weight of the truck vertically down. You have the normal force perpendicular to the surface. So this is the normal force. And of course, the friction force is in direction opposite to the direction of motion. So this is kinetic friction in this direction. In this coordinate system, it is convenient to decompose the weight into a component that is perpendicular to the surface and a component that is parallel to the surface. So here is the decomposition of the weight into those two components. So the red component is perpendicular to the pavement. And the other red component is parallel to the pavement. The angle between them, of course, is 90 degrees. So looking at this, you realize that the angle of the incline is going to appear right here. This is the angle theta is going to be here. And I need this angle theta in order to say that this component of the force of gravity is going to be equal to the hypotenuse mg multiplied by cosine of the inclined angle. In magnitude, that component, y component of gravity, has to be equal to the normal force so that truck not to fly above the pavement or sink below the pavement. In other words, this diagram tells me that the normal force acting on this truck in magnitude is equal to mg times cosine of the angle of incline. From here, I know that the friction force is coefficient of friction, this is kinetic friction, coefficient of kinetic friction times normal force, which means that I can express the kinetic friction force as coefficient of friction times mg times cosine of the angle theta. And once I have the value of the force, I can say the work done by the friction force is equal, by definition, to the value of the friction force times the value of the displacement times the cosine of the angle between the displacement vector and the friction force. The friction force is this way, the displacement vector is this way. The angle between them is 180 degrees, and cosine of 180 degrees is -1, which means that the work done by the friction force is going to be negative, well, friction force itself, which is coefficient of friction times mg times cosine of theta times the displacement x. This is the work done by the friction force. Well, now I put the things together. The change of energy is, right, this is 0. The change of energy is negative initial energy. So the change of energy is negative 1/2 mv initial squared plus mgh. Oh, well, let me rewrite it like 1/2 mv initial squared plus mg x times sine the angle theta. So this is the change of energy. And the work done by the friction force, the external non-conservative force, is this. So it is negative coefficient of friction times mg times cosine of theta times displacement. And from here, you can calculate the stopping distance x. So this expression, if you reach this expression, you can answer any variation of the problem. Well, if the truck was moving uphill, you're going to have some different algebraic signs, but the idea is going to be similar. Well, for the moment here, we're looking for the displacement x. Everything else is known. The mass of the truck is not known, but it is in every term and it cancels out. The negative signs, you can get rid of the negative signs also. And the equation that you are going to have is going to look like this. After you change the negative signs to positive, okay, let's do it in 2 steps. You're going to have 1/2 v initial squared plus gx sine of theta is equal to coefficient of friction times g times cosine of theta times x. And the 2 terms that contain the unknown x are here. You have to bring them to one side of the equation. Let's say move this to the other side with opposite algebraic sign. You're going to have 1/2 v naught squared is equal to coefficient of friction g times cosine of theta times x minus g times x times sine of theta. Factor out the common factor on the right-hand side of the equation and write the right-hand side first. So the common factor is the unknown displacement x, and you can factor out also 9.8. In the brackets, you're going to have coefficient of friction times cosine of the angle of incline minus sine of the angle of incline. And this should be equal to v naught squared divided by 2. And now solving for the unknown distance x, you get that the displacement x is equal to v naught squared divided by 2 times g times coefficient of friction times cosine of the angle minus sine of the angle. And this should be the answer here. So using work energy theorem requires multiple steps, but you can solve the same problem using Newton's second law, which also is going to require multiple steps. It's going to be about the same length, maybe a little bit longer. So again, this problem is going to be available upon request. But it is going to be a version of that problem, not identical. So you may be given, let's say, the stopping distance, and you may want to find, let's say, the initial velocity. And if you reach this equation, you can immediately solve for initial velocity. Or another variation would be the truck to be going uphill, and other combinations of those variations. If you don't, well, it's a good exercise to solve the same problem using Newton's second law, but let's restrict ourselves with a single way of doing it. Let's see connections and remarks, questions about this problem first. If not, yeah.
So what would be the difference if it was going up?
Well, if it is going uphill, and again, let's say you start with some initial velocity, your initial energy is going to be zero gravitational potential, but non-zero kinetic, 1/2 MV not kinetic. Your final energy is going to be, if you're at stop, only gravitational potential, it's going to be mgh. So the final is going to be, in that case, mgh. The initial is going to be this term. And again, you have to find the change, final minus initial, and again, work out. It's going to be very similar steps. Okay, and let's do the next problem. Problem number 16 is ballistic pendulum. And it is the last problem. And again, problem number 16 was given several times on the final for the lab. And I also have given it in the final for this class when I taught this class some years ago. So it is a problem that is easy and at the same time requires you to understand the concept of energy and also the collisions of completely inelastic collisions. So you can start this problem. You can start this problem. If you start it backwards, you can answer part A immediately. So look, you have a collision, and at the instant immediately after the collision, the object has total mass, sum of the two masses, and it is at that instant it is in motion with some unknown speed. They say that the unknown speed, you have to find it eventually, the final. So during the collision, you lose some kinetic energy. Actually, you lose a lot of kinetic energy during the collision. But whatever energy is left after this collision, that kinetic energy is going to be transformed without any losses into gravitational potential energy. In other words, immediately after the collision, the energy is kinetic, purely kinetic, and therefore it is 1/2 the mass is a combined mass because the two objects stick together. And the speed is unknown speed v. You have to square it to get kinetic energy. So this is the energy, the kinetic energy left in the system after the collision. And that kinetic energy without losses is transformed into gravitational potential energy, which is mass, in this case, the combined mass, times g times h. They give you the height 0.5. So everything is known. You can even cancel the combined mass, and you get that the final energy is equal to square root of 2gh. So this is your answer for part A. Part B, find the speed of the bullet before the collision. So the collision is completely inelastic. That collision doesn't conserve energy. Mechanical energy is lost during this collision. But linear momentum is conserved. You want the linear momentum of the system before the collision to be equal to the linear momentum of the system after the collision. Again, vector signs are not necessary because all vectors are going to be in horizontal direction. Before the collision, the linear momentum is only due to the moving bullet. The block is at rest. Therefore, before the collision, the linear momentum is the mass of the bullet multiplied by the unknown speed. multiplied by the unknown velocity of the bullet. This is the initial linear momentum. After the collision, you have a single composite object with mass m1 plus m2, and it is moving with speed v final that you just calculated. So from here, the only unknown is the speed of the bullet, and you can solve for that speed. And you get that, you get from here, you immediately say the speed of the bullet before the collision is equal to m1 plus m2 divided by m1, and all of this multiplied by the speed of the system immediately after the collision, which you calculated in part A. So this is the answer for part B. Part C is asking you what percentage of the initial kinetic energy is lost. So the initial kinetic energy is only due to the bullet. The block is at rest, so its kinetic energy is 0. So the initial kinetic energy, the initial, call it kinetic energy initial. The final energy of the system eventually becomes gravitational potential. So initial minus final which is m1 plus m2 times gh, let's say. This is the lost energy. Divide what fraction of the initial. So what the initial energy is kinetic energy initial. So they want you to calculate this fraction, where the initial kinetic energy we said is only due to the moving bullet. So this fraction that they want you to calculate is 1/2 the mass of the bullet times the initial speed of the bullet squared minus m1 plus m2 times gh, all of this divided by 1/2 initial kinetic energy of the bullet. So here everything is known. Well, you can simplify it if you want. Okay, let's simplify it because it is the last problem. This first term divided by this is 1 minus, so you're going to, when you do the division, you're going to have 2 times m1 plus m2 times gh divided by m1 times v initial 1 squared. And you can substitute v initial 1 squared here and do more simplifications, but it is more convenient directly to do numerical substitutions here. So this is your answer. Whatever number you get, you have to multiply it by 100 in order to get in percent, the answer in percent. And they say that you lose, after you do the substitution, you lose something like 99% of the energy is lost during this collision. Only 1% is left after the collision. Okay.
Can you explain why that the final energy of the system is the gravitational potential?
Look, this here is, it is, yeah, this is a good question, actually. I probably shouldn't have written it this way, but it was easier for me to write it this way. Look, final energy of the system, immediately after the collision, the system is right here and at 0 height and moving with speed v final that we calculated. That energy without losses is transformed into gravitational potential energy. With no losses because there are no any external forces when this pendulum swings. So all of the energy, and this is how we started. We say the final energy of the system immediately after the collision is equal to gravitational potential energy. So I should have written here this second term, I could have written it this way. But this is simpler and you don't need to do substitution, square root and things like that. So this is why I wrote it this way, but it is a bad style. Right, you could have written it like this. And after that, another step, substitute that with its equal, which is simpler to calculate. Is it kind of clear or not quite? Okay, let's see any other questions related with this midterm, chapters 5, 6, 7, 8. If not, let's stop here and I'll see you on Friday. The test is going to be easy, but you really have to, the calculation of problems, you have to show logical, clean, step-by-step solution. Okay. Okay.